Welcome to the Deep Dive, your shortcut to being genuinely well-informed, packed with surprising facts and just enough humor to keep you hooked.
In each deep dive, we take a stack of your sources, articles, research, your own notes, and we extract the most important nuggets of knowledge or insight.
We act as your expert guides to help you understand what's truly important.
Today we're embarking on a pretty ambitious exploration. We're looking into the architecture of some of the most dynamic and complex online platforms that power our digital world.
Yeah, we'll be breaking down how systems like, popular coding platforms, live comment feeds, those vital notification services.
Fast-paced online auctions, secure payment gateways, traffic-controlling rate limiters, lightning-quick stock trading apps, and even personal fitness trackers are designed and built. It's quite a list.
Get ready for some serious aha moments. We're going to distill complex system designs into clear, actionable insights, providing you with a thorough understanding without, hopefully, the information overload.
Right. You'll gain knowledge quickly but thoroughly, appreciating multiple perspectives on these intricate challenges.
Our approach for this deep dive is clear. We'll tackle each system one by one, methodically.
Exactly. We'll dissect its functional requirements, what it does and its non-functional demands, how well it performs and behaves.
Then we'll identify its core entities, understand its API interfaces, examine its high-level architecture.
And then, crucially, dive deep into specific design challenges and their ingenious solutions. No mixing topics or skipping ahead, just focused learning for each fascinating system.
All right, let's unpack this. First up, let's dive into the fascinating world of designing a coding platform, something like LeetCode.
Right. Imagine a global coding competition, maybe tens of thousands of participants, all submitting their solutions at, the same time.
How do you instantly grade their code, keep it fair, and most importantly, prevent anyone from trying to, compromise your servers? That's the core puzzle we're looking to solve here. #1 functional requirements.
Okay, so to begin, we need to understand the fundamental actions users must be able to perform, the functional requirements.
Right.
First and foremost, users need to be able to view a list of coding problems. This is their entry point,
Yeah.
where they discover challenges tailored to their learning or competition needs.
Like browsing a big catalog of challenges.
Exactly.
And once they've picked a challenge, they must be able to view a given problem and code a solution in multiple languages.
And this isn't just a simple text box, right? It requires a robust, interactive in-browser code editor that actually facilitates coding.
Yeah, with features like syntax highlighting and maybe other stuff you'd expect from an IDE, an integrated development environment.
Correct. The next crucial step in this interactive loop is for users to be able to submit a solution and get instant feedback.
That instant feedback part is key, isn't it?
It is. It implies rapid execution and evaluation of the submitted code, telling them whether their solution passed or failed, almost immediately.
And for those who thrive on competition, users should be able to view a live leaderboard for competition.
Oh, absolutely essential during live coding events. It fosters engagement and provides those immediate ranking updates that keep everyone on their toes. #tag2, non-functional requirements.
Okay, so beyond what it does, how well does the system need to perform? These are our non-functional requirements.
Right. First, the system must prioritize availability over consistency.
What does that mean exactly?
Well, in essence, it's more critical for the platform to always be accessible and running, even if there are slight momentary delays in data synchronization.
Ah, okay. So like a brief inconsistency, maybe the leaderboard not updating for a split second, that's generally acceptable if it means the whole system stays online.
Precisely. It ensures users can always submit their code.
Security is paramount here, I imagine. The system must support isolation and security when running user code.
Absolutely critical. User-submitted code is untrusted, so it must be executed in a completely isolated and secure environment, a sandbox.
This prevents malicious code from affecting the host system, stealing data, or messing with other users, right?
Exactly. The risks of a user breaking out of their designated sandbox are severe, so robust security measures are non-negotiable.
And connecting back to that instant feedback requirement.
The system must return submission results within 5 seconds. This low latency is vital for a good user experience, especially in competitive or learning settings where immediate validation is expected.
Waiting longer than that would get pretty frustrating fast.
Definitely. And finally, scalability. The system needs to scale to support competitions with 100,000 users.
Wow, that outlines the immense challenge of designing a system that can handle a massive flood of concurrent users, particularly during those big competitions, without any performance slowdown.
It's all about being ready for those peak loads, ensuring everyone has a smooth experience. Hashtag tag tag 3. Core entities.
Let's define the foundational data elements, the core entities for this platform.
Okay. First, we have the problem entity. This encapsulates everything about a coding problem. The problem statement itself, all the accompanying test cases, which are crucial input-output pairs,
Right, the things you test against.
and the expected output for those test cases. This forms the definitive basis of what users are trying to solve.
Got it. Then there's the submission entity. This stores the user's actual code submission exactly as they wrote it.
And, critically, the result obtained after running that code against the predefined test cases. It's the complete record of each attempt and its outcome.
Makes sense. And finally, the leaderboard entity.
This one's pretty straightforward. It stores and manages the rankings for competitions. Its purpose is to track and display the current standings for ongoing competitions, directly linking back to our functional requirement for a live leaderboard. Hashtag 4 API or system interface.
Okay, so to interact with these entities and let users do things, we need a clear set of application programming interfaces or APIs.
Yeah.
For viewing a list of problems, we'd have an API endpoint just for fetching that entire catalog of coding problems, maybe with options for filtering by language, difficulty, tags, that sort of thing.
Makes sense. And when a user wants to delve into a specific problem, there'd be another API endpoint to retrieve the full details of that single problem.
Like the complete problem statement. Any examples?
Exactly. Example inputs, outputs, other relevant info.
Now, for the core action of submitting a solution, there's an API endpoint for users to send their coded solutions for evaluation.
Right. And this is where that security note comes in.
Yeah, this is crucial for system design generally, and it applies here. When we design this API, we assume the user is authenticated, and their unique ID, the user ID, is stored securely in their session.
You should never pass user ID or timestamps directly in the body or query parameters of an API request, ever.
Right. User data should always be passed securely in the session or via something like a JSON web token, a JWT, while timestamps should always be generated by the server.
It's a fundamental security best practice. Prevents tampering, ensures data integrity.
Okay, good point. And finally, to view a live leaderboard for competitions.
There's an API endpoint specifically for retrieving that real-time leaderboard data for specific competitions, ensuring users get the most up-to-date rankings. Hashtag 5. High-level design.
Let's piece together how these components interact at a high level, addressing our functional requirements. To allow users to view a list of coding problems, we'd probably choose a NoSQL database, something like DynamoDB.
Right, NoSQL. Not only SQL, they store data in formats other than traditional tables, offering flexibility and scalability.
The thinking here is we don't need complex relational queries, and we can design the data by nesting test cases as a subdocument right inside the problem entity.
Which simplifies data retrieval, keeps all the related problem info together. Smart.
Next, for users to be able to view a given problem and code a solution, we would integrate the Monaco editor.
Yeah, that's not just a basic text area. It's a sophisticated, feature-rich code editor. Lets users code right in the browser.
With syntax highlighting, auto-completion, other IDE-like stuff, makes for a much better user experience.
Definitely. Now, for users to submit their solution and get instant feedback, we have two main ways to execute that untrusted user code.
Okay, what are they?
The first, and a very common solution, is to run code in a container, specifically Docker. We'd create pre-built Docker containers for each supported language, Python, JavaScript, Java, whatever, with all necessary dependencies pre-installed.
And the user's code runs inside one of these containers.
Exactly, in a sandboxed environment, meaning it's isolated from the main system.
Okay.
And a key insight here is that instead of spinning up a whole new virtual machine for each submission, which would be slow and expensive, we can reuse these containers for multiple submissions.
Ah, that drastically reduces resource usage and improves performance. Clever.
It does. But it comes with challenges. Containers share the host OS kernel, so you need proper configuration and security to prevent users from breaking out of the container and getting unauthorized access.
Right, the sandbox needs strong walls.
And you must enforce strict resource limits, -EPU memory, to stop any single submission from hogging resources and impacting others. That's a potential denial of service risk.
Okay, so what's the alternative?
The alternative is a serverless function approach. Here, you run user code in a serverless function, like AWS Lambda.
Serverless functions. Those are the small, stateless, event-driven bits of code managed by cloud providers, right?
Exactly. We'd create a serverless function for each supported language, install dependencies. When a user submits code, we trigger the appropriate function to run it and return the result.
Interesting. Okay, and lastly, for users to view a live leaderboard for competitions.
A direct, normal query to the entire database table for leaderboard data would quickly become really inefficient, especially with lots of users or frequent updates.
Right. That highlights a key optimization challenge we'll need to tackle. Hashtag 6, deep dives. Now let's really get into the nuances with some deep dives, starting with one of the most critical aspects for any code execution platform. How will the system support isolation and security when running user code? This is paramount, like you said.
To get robust isolation, we use several techniques. First, a read-only file system. We mount the code directory as read-only and direct any output to a temporary directory that gets deleted shortly after execution.
So they can't write persistent data or modify things.
Precisely. It significantly enhances security. Second, we enforce CPU and memory bounds, strict limits on how much CPU and memory a container can use.
And if they exceed it?
The container is immediately killed, prevents resource exhaustion that could impact others, or the host system.
Got it.
Third, an explicit timeout, essential to prevent infinite loops. We wrap the user's code in a timeout that kills the process if it runs too long, say longer than 5 seconds.
Which also helps meet that non-functional requirement for results within 5 seconds.
Exactly. Fourth, and crucially, we limit network access. We completely disable network access within the container. Users cannot make external calls.
How do you enforce that?
If you're on AWS, for instance, you'd configure VPC security groups and network access control lists, NACLs, to restrict all outbound and inbound traffic, except for maybe essential internal connections. Prevents code from accessing external resources or leaking data.
Makes sense.
And finally, we implement no system calls, specifically using SACOMP.
SecOmp, secure computing mode.
Yeah, it's a Linux kernel feature.
Yeah.
It lets a process restrict the system calls it can make. We configure it to severely limit what the container can do, preventing operations that could compromise the host. Adds a powerful layer of defense.
Okay, that's a comprehensive security approach. Next, deep dive. How would you make fetching the leaderboard more efficient? That direct database query sounded like trouble.
It would be. The elegant solution here involves Redis sorted sets with periodic polling. Redis is incredibly fast. It's an in-memory data structure store.
So not the main database.
Right. The core idea is to use Redis's sorted sets, which are specifically designed for ranked data, to maintain a real-time leaderboard. We still store the full, persistent submission results in our main database, though.
So when a submission is processed, you update both.
Exactly. Update the main database for persistence and update the Redis sorted set for the live ranking.
And on the client side, how do they get the updates?
They don't need constant streaming. Instead, clients can just poll the server for leaderboard updates at a set interval, maybe every 5 seconds.
And the server just pulls from Redis?
Yep. The server retrieves the top end users from the Redis sorted set. This retrieval is, well, wicked fast, because Redis operates entirely in memory. It completely avoids any expensive, complex queries on the primary database.
Is there a specific command for that?
Yeah, the specific Redis command might be something like zrevrange competition.leaderboard.competition ed n1 with scores. This efficiently fetches a range of elements, ordered by score in reverse, along with their scores.
Right, and you can adjust the polling interval easily.
Absolutely. If 5 seconds is too frequent or not frequent enough, we can easily adjust it without significantly impacting core system performance.
Now, the big question for any competitive platform. How would the system scale to support competitions with 100,000 users? That's a lot of people hitting the system at once.
Honestly, 100,000 concurrent users, while substantial, is still quite manageable for well-designed, modern distributed systems. Our API server, through horizontal scaling, should handle this load effectively.
Horizontal scaling just means adding more instances of the server behind a load balancer, right?
Exactly. Distribute the incoming traffic. Beyond the API server, we can horizontally scale each of the language-specific containers that execute the code.
So multiple container instances per language.
Yep. Spin up multiple instances for Python, Java, etc., and distribute user submissions across them. This can be dynamically managed through auto-scaling groups, adjusting the number of active instances based on traffic, CPU, or memory metrics.
But there's a risk of wasting resources if you spin up too many.
There is. You could end up wasting resources and incurring unnecessary costs if the scaling isn't tuned well.
So is there another way?
As an alternative, or maybe an enhancement, we can introduce a message queue like Amazon SQS, which is a managed queue service, between the API server and the containers.
A queue. like a buffer.
Exactly. The queue acts as a buffer, absorbing and temporarily storing submissions during peak times. This prevents the code execution containers from getting overwhelmed.
But introducing a queue makes the system asynchronous, doesn't it?
It does. Crucially, this means the API server can no longer return immediate results for submissions. The user will need to poll the server for their results later.
Trade-off.
A trade-off, yes, but a significant benefit is that the queue also enables automatic retries if a container fails, which greatly enhances reliability.
Okay. Finally, let's look at a critical development challenge. How would the system handle running test cases? Specifically, running the same tests against code in different languages without creating a maintenance nightmare.
The core insight here is that you absolutely do not want to write a separate set of test cases for each problem in each programming language you support.
That sounds awful.
It would be an absolute nightmare to maintain. Multiplying your effort by the number of languages? No way. Instead, you write a single, universal set of test cases per problem that can then be run against any language.
How does that work? How can Python code run the same tests as Java code?
You get a standard way to serialize the input and output of each test case. This could be a universally understood format like JSON or maybe protocol buffers, something language agnostic.
Okay, so you have the tests in a standard format. Then what?
Then for each supported language, you need a test harness. This is a small piece of code specific to that language.
A test harness. What does it do?
Its job is to deserialize those generic inputs from a standard format, pass them correctly to the user's submitted code, execute that code, and then compare the actual output of the user's code to the deserialized expected output from the test case.
So the harness is the language-specific adapter.
Exactly. This ingenious approach allows a single set of test logic to validate solutions across all supported languages efficiently. It's much more maintainable.
All right, let's shift gears. Big time. We're diving into another real-time challenge, designing Facebook's live comment system.
Oh yeah, imagine watching a live video stream where thousands, maybe tens of thousands of comments are just flying by every second.
How do you make sure everyone sees the latest comments instantly without overwhelming the system or, missing out on the conversation? #1 functional requirements.
Okay, first off, the most basic capability. Viewers can post comments on a live video feed.
Simple enough. Let people type things.
It's the fundamental ability for users to contribute text comments to an ongoing live video stream.
Then, crucially for a live experience, viewers can see new comments being posted while they are watching the live video.
Right. This emphasizes the real-time or near real-time nature of comment delivery. Absolutely vital for an immersive, connected experience.
And it's not just about what's happening now, right? Viewers can see comments made before they join the live feed.
Exactly. This addresses the need for historical context. Lets new viewers catch up on earlier discussions without feeling lost or losing continuity. #tag2. Non-functional requirements.
Okay, from a non-functional perspective, the scale here is just immense. The system must scale to support millions of concurrent videos and thousands of comments per second per live video.
Yeah, that highlights the enormous challenge, handling a massive number of simultaneous streams and a very, very high volume of comments pouring in.
And similar to the LeetCode platform, the system should prioritize availability over consistency. Eventual consistency is fine.
Right. In a live comment feed, it's far more important for the system to always be up and available, even if comments might appear slightly out of order or with a brief delay across different viewers.
So, stripped instant consistency for every single comment isn't the top priority.
Less critical than ensuring continuous operation, yeah. Eventual consistency works here.
Okay. And finally, we need low latency broadcasting comments to viewers in near real time. Specifically, targeting less than 200 milliseconds end-to-end latency under typical network conditions.
That's a very specific target. It's crucial for the live video experience. Any significant delay would make the comments feel disconnected from the video itself, undermining that live feel. #3. Core entities.
Let's define the fundamental entities for this system. First, the user entity.
Pretty simple. A user can be either a viewer watching the live video or a broadcaster streaming it.
Then there's the live video itself. This represents the actual video stream being broadcast.
Right. And it's important to note, this entity is typically owned and managed by a different team, probably the core video streaming platform. But it's central to our comment system. We need to integrate with it.
It's the stream around which all comments revolve.
Exactly. And finally, the comment entity.
The core content, the actual message posted by a user on a live video, the specific text entry.
That's the one. #HTAG4 API or system interface.
To enable these interactions, we'd have a fairly straightforward set of APIs for creating a comment.
There would be an API endpoint that users hit to submit their new comments to a specific live video. A POST request, probably.
And to fetch past comments?
We have another API endpoint specifically designed for retrieving older comments, necessary for users who join late or want to scroll through the history. #tag 5, high-level design.
Let's outline the high-level architecture. First, addressing how viewers can post comments on a live video feed for the comments database.
We'll choose DynamoDB again, a NoSQL database. It's selected for its speed, massive scalability, and high availability. Perfect for handling a high volume of comment writes.
Okay, so the flow for posting a comment would be user drafts a comment on their device, the commenter client.
Then the client sends this comment to the comment management service via a standard POST comments.liveVideoID API endpoint.
And finally, the comment management service receives it and stores the comment in DynamoDB.
Efficiently, yes.
Now, for viewers to see new comments being posted while they are watching the live video, we said polling is bad.
Yeah, a simple polling mechanism would quickly run into severe limitations. As comments and viewers grow, the polling frequency would need to increase like crazy.
Which would put a huge strain on the database and lead to tons of wasted requests.
Exactly. It's just inefficient for high-volume, real-time needs. We need something better.
Okay. And to handle viewers seeing comments made before they join the live feed, they need to scroll up, right?
Right. Users should be able to scroll up to view progressively older comments. The UI pattern is often called infinite scrolling, common in chat apps.
And to achieve this efficiently, we need pagination, breaking up that huge list of comments into smaller chunks.
Exactly. And there are two main approaches, offset pagination and cursor pagination.
Which one's better here?
The better approach for high-volume, constantly updating data like comments is cursor pagination.
Cursor pagination, that uses a unique identifier, a cursor, to mark the starting point for the next chunk.
Precisely. It specifies the exact starting point for fetching a new set of results. Initially, the cursor is the most recent comment, and it updates as the user scrolls.
Why is that more efficient?
Because the database doesn't need to count through all the rows before the cursor for each query, especially if you have an index on the cursor field. Offset pagination has to count, which gets slower and slower the further back you go.
Oh, got it. And it's more stable, too, like if comments get added or deleted while scrolling.
Exactly. The cursor still accurately points to the correct item. An example request might look like getComments.liveVideoID.cursor, last commented in page size 10.
And since we chose DynamoDB,
We can natively use the last commented as the cursor via DynamoDB's last evaluated key feature. It's built for efficient cursor-based queries. #tag 6. Deep dives.
let's get into the deep dives. Starting with a crucial question for live systems. How can we ensure comments are broadcasted to viewers in real time if polling is out?
Right. First, let's discuss why WebSockets, even though they're a common real-time tech, are not necessarily the best fit here.
Really? Why not?
Well, WebSockets are great for applications with a balanced read-write ratio, like a two-way chat where both sides send and receive data frequently.
But for live comments, the ratio is really unbalanced. Lots of readers, fewer posters.
Highly unbalanced, exactly. Comment creation is relatively infrequent compared to the sheer number of viewers reading comments. Most viewers never post.
So opening a persistent two-way WebSocket for every single viewer is inefficient. Lots of overhead.
Precisely. High connection maintenance overhead when most clients are just consuming data. Doesn't make sense.
Okay, so what's the better solution?
Server send events, or SSE. SSE is a persistent unidirectional connection over standard HTTP. Simpler to implement than WebSockets too.
Unidirectional.
Yeah.
So the server pushes data to the client.
Exactly. The server pushes data to the client in real time, while any client-to-server communication happens through regular HTTP requests.
Ah, so that fits our unbalanced ratio much better. Infrequent comment creation uses HTTP POST. Frequent reads use SSE's efficient one-way streaming.
Perfect fit. However, SSE does have its own challenges. Browsers typically limit concurrent SSE connections per domain, and connections might get terminated by proxies or load balancers due to inactivity. You have to handle that.
Okay, so the updated flow for real-time broadcast would be, first, user posts a comment, it gets persisted to the database.
Second, for everyone else to see it, the comment management service sends the new comment over SSE to all connected clients subscribed to that live video.
And third, the commenter client receives the comment and immediately adds it to the viewer's comment feed. Simple enough flow.
Conceptually, yes. The scaling is the hard part.
Right. Next massive challenge. How will the system scale to support millions of concurrent viewers?
With SSE being the tech, we hit that scaling problem. Each viewer needs an open connection, millions of connections. A single machine can't handle that. We need horizontal scaling, more servers.
And the core problem across servers is, if viewers of the same video connect to different servers, how does a new comment reach all of them? User A on server 1, user B on server 2 watching the same video.
Exactly. How do we ensure user B sees the comment posted via server 1? We have several approaches. Approach 1 is intelligent routing at the edge. Using load balancer to route users based on the video they're watching, trying to co-locate viewers on the same server.
Okay, how?
Option A within that is consistent hashing, layer 7. A layer 7 load balancer, like NGINX or Envoy, looks at the request, finds the live video ID, maybe in a header or URL path, and uses a consistent hashing function to route all viewers for that same video ID to the same backend server.
Benefit: keeps related viewers together, reduces server overhead.
Correct. Option B is dynamic lookup using a coordination service. Here, the load balancer queries a separate service, like Apache Zookeeper, which maintains a dynamic map of which server is currently assigned to handle each live video ID.
That sounds more flexible. Mappings can change in real time.
It is more flexible. But the drawback is added operational complexity. You need robust caching and failure handling for that coordination service itself.
Okay, what's approach 2?
Approach 2 is the pub-sub model. Using a publish-subscribe system, each real-time messaging server subscribes to specific topics, essentially, one topic per live video. They receive comments as they're published to those topics.
So the comment creation service just publishes to the topic and doesn't care which server gets it.
Exactly. It decouples creation from delivery. The correct servers subscribe to that topic, pick it up, and fan it out to their connected clients.
But choosing the right pub-sub system matters, right? Kafka versus Redis.
Big time. Kafka is highly scalable, fault-tolerant, persistent messages. Great for durability. But generally higher latency and can struggle with very rapid dynamic user subscriptions, like quickly joining and leaving video streams.
And Redis pub-sub.
Very low latency, fire and forget because it's in memory, but the drawbacks are significant. Typically no message persistence, potential data loss if a server hiccups, and memory limits can hinder scalability for huge numbers of topics or messages.
Okay, any other approaches?
Approach 3 is the dispatcher service, which is kind of an inverted model. Instead of servers subscribing, a central dispatcher service directly routes new comments to the correct server.
How does that work?
Real-time messaging servers register themselves with the dispatcher, telling it which live video ads they're handling. The dispatcher maintains this dynamic map of live video ID to the responsible server. When a new comment comes in, it goes to the dispatcher, which looks up the correct server and forwards the comment directly.
What are the challenges there?
Mapping accuracy. Keeping that map constantly up to date is hard, especially during rapid traffic shifts. And consistency. If you have multiple dispatcher instances for redundancy, their maps must be perfectly synced, often needing another coordination service like Zookeeper or etc. Adds complexity again.
So to wrap this up for, say, a system design discussion.
Both PubSub with viewer co-location and the dispatcher service are valid advanced solutions. PubSub is generally seen as easier to implement with fewer tricky edge cases, making it a safer, more common choice to discuss.
The key is showing you understand the need to either co-locate viewers or have efficient communication between servers, and outlining some high-level ways to achieve that massive scale.
Exactly. Demonstrate you grasped the core distribution problem.
Okay, our next deep dive takes us into the subtle yet absolutely crucial world of asynchronous communication. Designing a notification service.
Right. Think about all those transactional alerts, system updates, marketing messages you get every day. This kind of system is the engine behind them. ###1. Overview.
So what's its purpose?
This system is specifically designed for the asynchronous delivery of notifications from publishers, the sender, to subscribers, the recipient.
And the key design principle is decoupling.
Exactly. It decouples senders from receivers using a topic-based publish-subscribe model. Publishers send messages to a topic, subscribers receive messages from topics they care about.
Which allows for high scalability and reliability for all sorts of use cases. Transactional alerts, updates, marketing.
Correct. And the architecture guarantees at least once delivery, meaning a message gets delivered at least once, maybe more if there are retries. It's built to be horizontally scalable and fault-tolerant. It can grow and stay robust under stress. ###2. System architecture and data flow.
The architecture is composed of several decoupled microservices, right? Each handling different stages.
That's the idea. For the ingestion phase, a client's request to publish a message first hits a load balancer.
Which then routes it to a stateless front-end service.
Yep. During validation and persistence, this front-end service handles authentication, validates the request data, and performs deduplication.
Deduplication, how?
By checking a unique request ID against a cache like Redis. Prevents processing the same message multiple times if the client retries.
Smart, then if it's valid.
It publishes the message to a message queue. And crucially, it sends an immediate HTTP 202 accepted acknowledgement back to the publisher.
So the publisher knows it's been received and will be processed even if it hasn't been sent yet.
Exactly. The decoupling aspect is mainly handled by the message queue itself, maybe Apache Kafka or AWS SQS. It's the system's backbone.
It stores messages durably, absorbs traffic spikes, and decouples ingestion from the sending logic.
Precisely. The system can keep accepting messages, even if the sending part is temporarily overloaded.
Okay, then for processing and dispatch, we have the sender service.
Right. This is a pool of consumers that continuously polls the message queue for new messages, for each message it gets.
It checks who needs to receive it.
Yeah, it queries the metadata service to get the list of subscribers for that message's topic. Then it creates parallel delivery tasks for each subscriber.
Parallel delivery, nice. And then it calls the right downstream service. Email, SMS, push notification.
Exactly. It invokes the appropriate service to deliver the message through the correct channel.
And lastly, metadata management is handled by the metadata service.
Correct. Its purpose is to manage all the info about topics and subscriptions. It's backed by a scalable NoSQL database like Cassandra or DynamoDB to handle lots of data.
And uses heavy caching for speed.
Heavy caching, yes. To ensure low latency responses to both the front end and sender services, minimizing direct database hits. #tag3. Component deep dive.
Let's delve deeper into specific components, starting with the API design. It's RESTful APIs.
Yep. Simple set of RESTful APIs. You'd have a post topics to create a new topic.
Then post topics name, publish to publish a message to a specific topic.
Right. To subscribe, PST topic name subscribe initiates a subscription, usually triggering a confirmation flow.
Like sending an email with a link.
Exactly. And get subscriptions token confirm is used to confirm that subscription using the unique token from that link.
Okay. What about the storage strategy? Two main parts.
Yes. For the message queue, which is temporary message storage, a distributed log like Apache Kafka is ideal.
Why Kafka specifically?
It's designed for streaming. It provides out-of-the-box durability via replication, partitioning for parallel consumption, and persistence for handling retries. It's generally superior to a generic NoSQL DB for this kind of streaming workload.
Got it. And for the metadata database, storing topics and subscriptions.
A partitioned NoSQL database like Apache Cassandra or Amazon DynamoDB is a perfect fit. Data can be sharded horizontally, divided by topic name, or subscriberid for horizontal scalability.
Meaning it can grow by just adding more nodes.
Exactly. And that caching layer, like Redis within the metadata service, minimizes direct database hits for low latency lookups.
And what about handling failures and retries? The guarantee is at least once delivery, right?
At least once delivery. That's the core principle. From the publisher to the queue, if the front-end service fails to publish, it can retry. The publisher client should also have its own retry mechanism.
Double protection, and from the queue to the subscriber.
If a sender service instance fails delivery, the message isn't lost. It stays in the queue and will be picked up again by another sender instance after a visibility timeout.
A visibility timeout.
Yeah, a configurable period where the message is hidden from other consumers, giving the first one time to process or fail.
What about messages that just keep failing? Poison pills?
For those, we use a dead letter queue, or DLQ. Messages that fail delivery repeatedly, exceeding a retry limit, are automatically moved to a DLQ.
Which prevents them from blocking the main queue.
Exactly. And it allows engineers to inspect them manually and figure out why they're failing.
And finally, slow subscribers. Does one slow endpoint hold everything up?
No, because delivery tasks run in parallel. A single slow or unresponsive subscriber endpoint won't impact delivery speed for others. Parallelism prevents bottlenecks. #tag4. Key system requirements and solutions.
Now let's summarize the key system requirements and their solutions concisely. For scalability.
The solution is that all components, front-end, sender, databases, queue, are stateless and horizontally scalable. Just add more instances. Data is partitioned efficiently.
For high availability.
Avoid single points of failure. Multiple instances of each service across availability zones. Message queue and NoSQL DB replicate data across multiple nodes. If one fails, the system keeps running.
For durability.
Messages are persisted in the message queue immediately on receipt. They're not deleted until successful delivery is confirmed. Ensures no message loss, even if a sender instance fails mid-process.
For security.
TLS encryption for data in transit. Data at rest encrypted in the DB and queue. All API endpoints enforce strong authentication and authorization. Controls who can publish or subscribe.
And lastly, for monitoring.
Each service emits vital metrics: latency, throughput, errors, real-time view of system health, comprehensive audit logs for API usage and delivery status, processed by a separate logging pipeline to avoid impacting core services.
Okay, let's pivot to the dynamic world of online commerce. Our next system. Designing an online auction platform, much like eBay.
Ah, yeah. Think about the thrill of bidding, those lightning-fast updates, and the absolute need for trust in every single transaction.
How do you build a system where everyone sees the same price at the exact same moment, and crucially, not a single bid is ever lost? That's the challenge. #1, functional requirement.
Starting with what users need to do. Functional requirements. Users should be able to post an item for auction with a starting price and end date.
The initial step for sellers. Item details, starting bid, how long it runs.
Exactly. Crucially, users should be able to bid on an item where bids are accepted if they are higher than the current highest bid.
The core bidding mechanism highlights that real-time validation rule. New bids must beat the current highest.
Right. And on the viewing side, users should be able to view an auction, including the current highest bid.
Defines the viewer experience. Need all auction details, with critical emphasis on displaying the most up-to-date highest bid. It informs their strategy. #2, non-functional requirements. Now for the non-functional aspects, this is where the financial nature really matters. The system must maintain strong consistency for bids to ensure all users see the same highest bid.
Absolutely vital for financial transactions. If different users see different highest bids. Chaos. Confusion, frustration, disputes. Everyone needs the exact same correct info, always.
Building on that, the system must be fault-tolerant and durable. We can't drop any bids.
Non-negotiable requirement. No bid can ever be lost, even if the system hiccups. Speaks directly to the integrity and trustworthiness of the whole auction.
To ensure fair play and responsiveness, the system must display the current highest bid in real time so users know what they are bidding against.
Reinforces that real-time visibility. Users need immediate updates to make informed decisions, react quickly to competitors.
And for a platform like eBay, the scale is huge. The system should scale to support 10 million concurrent auctions.
Massive challenge. Handling millions of simultaneous auctions, each maybe with many active bidders, without any performance slowdown. #3, core entities.
Let's define the core entities for our auction platform. First, auction represents the auction itself.
Includes starting price, end date, and crucially, a link to the item being auctioned.
Then there's the item, represents the thing being auctioned, physical or digital.
Includes descriptive info, name, description, image. Now, a key design insight here. We could embed item details directly in the auction entity.
But normalizing them into separate entities is better.
Yeah, significant advantages. Items can be reused across multiple auctions, like relisting unsold items. Item details can be updated independently. Easier to add item-specific features like categories or search without messing with the auction lifecycle.
Makes sense. Next, the bid represents a specific bid on an auction.
Includes the amount, the user placing it, and the auction it's for. Forms the essential audit trail of all bidding activity.
And finally, the user represents participants, either sellers starting auctions or bidders placing bids.
Simple enough. #4. API or system interface.
Defining our API endpoints. To create an auction, we'd have a POST request endpoint. Takes auction details, returns the created auction object.
Standard. For placing a bid, another POST request endpoint. Takes bid details, returns the created bid object, including its status accepted or rejected.
And for users to view an auction, a JET request endpoint, returning the full option and item details for a specific auction ID.
Straightforward. #5, high-level design.
Let's outline the high-level flow, starting with how users post an item for auction.
Okay. Client sends a POST request to auctions with auction details. API gateway routes it to the auction service.
Auction service validates, stores auction and item data in the database.
Database stores it in respective tables. Done.
Next, for users to bid on an item where bids are accepted only if higher than the current highest, the flow is.
Client sends a POST request to auctions.auctionedIdBids with bid details. API gateway routes to the bidding service.
Bidding service queries the database for the current highest bid on this auction.
Then it stores the new bid in the database with a status. Accepted if higher, rejected if not. Returns the status to the client.
And bids are stored in a separate bids table linked by AuctionID.
Exactly. Now, here's that important design decision again. Many might suggest just storing a max bid price field directly on the auction object instead of a separate bids table.
Seems simpler, maybe.
Seems simpler, but it violates a core principle. Avoid destroying historical data. Overwriting the max bid means permanently losing critical info.
Makes it impossible to audit the bidding process, investigate disputes, analyze behavior.
Exactly. The aha moment is, in a financial system, you need a complete audit trail. Inevitably, a user will complain their bid wasn't recorded, they should have won. Without a full history of every single bid, you can't prove them wrong or resolve disputes. Unacceptable.
Okay, strong point. Finally, for users to view an option, including the current highest bid.
When a user first views an option, they make a GET request to auctions.auctionID. Gets the auction and item details displayed.
But the problem is stale data. If the max bid price isn't refreshed.
Right. Users bid based on old info, get confused, frustrated when bids are rejected. Big problem in active auctions.
So the basic solution is simple polling. Check for the latest max bid price every few seconds.
That's the basic fix, yeah. Keeps the display updated, sets the stage for a better real-time solution we'll discuss in the deep dive. #6 deep dive.
Let's dive deeper. First, how can we ensure strong consistency for bids? We just talked about not just caching the max bid.
Right. We do store the max bid in the database, effectively using the option table as our definitive source of truth. But how do we handle concurrent updates safely? We use optimistic concurrency control, or OCC.
OCC, why is that a good fit here?
It's ideal because actual bid conflicts, simultaneous bids on the same auction at the exact same millisecond, are relatively rare compared to the total number of bids. Most bids won't collide head-on.
Okay, how does OCC work here, step by step?
First, you read the auction road to get the current maximum bid. This acts as the version in OCC.
Second, you validate that the new bid is indeed higher than this current max bid you just read.
Third, you try to update the auction row in the database, but only if the maximum bid value of the database hasn't changed since you read it.
How do you do that check?
Typically with a where clause check on the max bid value itself, or maybe a dedicated version number column. UP-Date-Auctions set max bid new bid where auctioned X, XA max bid, this old bidder rate.
Got it. And finally,
if the update succeeds, great. The bid record is then written to the bids table. If the update fails, meaning the max bid did change concurrently because someone else's bid got in first, the entire process retries from step 1. Read, validate, attempt update again.
okay, that handles consistency. Next deep dive. How can we ensure the system is fault-tolerant and durable? Cannot lose bids.
The solution starts with durable storage using a message queue. When a bid comes in, we immediately write it to a message queue like Kafka.
Why immediate to a queue?
Powerful insight. Even if the entire bid service crashes right after accepting the bid is safely stored in the queue. It won't be lost.
Ah, durability first. And it also provides crucial buffering against load spikes.
Exactly. Without a queue, under heavy load, we'd have to drop bids. Unacceptable. Crash. Unacceptable. Or massively over-provisioned servers. Expensive.
The queue acts like a buffer, holding bids until the bid service can process them. Makes surges manageable.
Precisely. Manages surge periods without constant over-provisioning. Plus, some queues, especially Kafka, offer guaranteed ordering.
Which is crucial for auctions, process bids in the order they arrived.
Right. So the flow of the message queue is user submits bid via API. API gateway routes to a producer, which immediately writes the bid to Kafka.
Kafka acknowledges the write, user gets a quick bid received response.
Yep. Bid service consumes the message from Kafka at its own pace. If the bid is valid, routes to the database using OCC.
And critically, if the bid service fails during processing,
the bid remains safely in Kafka, can be retried by another instance, or when the service recovers. No bids lost.
Excellent. Finally, how can we ensure the system displays the current highest bid in real time? Polling is basic. What's better?
Server-send events, SSE, provides a more elegant and efficient solution than constant polling.
SSE, again, establishes that unidirectional channel, server to client. Server pushes updates.
Exactly. Allows the server to push updates whenever they occur without client polling or heavier WebSocket connections.
So when a user views an auction, browser establishes an SSE connection. Server pushes new max bid values when they change.
Yep. Server side, we maintain active SSE connections per auction. New bid accepted. Push update to all connected clients for that auction.
SSE versus WebSockets here.
SSE is arguably a better fit. Communication is mainly one way, server to client for price updates, and SSE is typically lighter weight, easier to implement for this.
But the problem arises with multiple servers again, coordination.
Right. As users grow, need multiple SSE servers.
Hmm.
New bid hits server A. Users watching same auction might be on server B. Server A can't directly notify server B's clients.
So the solution is a pub subsystem.
Yes. Use Redis PubSub, Kafka, something similar. Need a way to broadcast the new bid to all relevant servers.
How does that work?
When server A receives the new bid, it publishes that bid to the PubSub system. All other bid service instances subscribe to the same channel.
They receive the message. If it's for an auction one of their clients cares about.
They send the new bid data down that client's SSE connection. Plus, enable auto-scaling to adjust the number of servers based on load dynamically.
Moving on to a critical piece of modern infrastructure, payment system design, inspired by companies like Stripe.
Yeah, imagine clicking Pay Now on a site. Behind that simple action is a world of complex interactions. Security, strong consistency, massive scalability, all converging.
How do you ensure every dollar is accounted for, never double charged, handled in milliseconds, and protect that super sensitive financial data? #, what is Stripe?
Right, so payment processing systems like Stripe, they allow businesses, we'll call them merchants, to accept payments from customers without building their own complex PCI-compliant infrastructure.
PCI, Payment Card Industry Data Security Standard. The rules for handling card info securely.
Exactly. The typical process. Customer inputs bank details on the merchant site. Merchant sends details securely to Stripe. Stripe processes, returns the result. #1. Functional requirements.
Okay, functionally. Merchants need to be able to initiate payment requests, basically charge a customer for a specific amount.
The core capability for a business to trigger a transaction.
And, of course, users should be able to pay for products with credit and debit cards, the primary payment method.
Yep, although many systems support others too. Lastly, merchants must be able to view status updates for payments. Things like pending, success, failed.
Crucial for their operations, tracking the life cycle and outcome of every attempt. #2, non-functional requirements.
Now for the non-negotiables in finance. The system must be highly secure. Absolute critical requirement. Compromise is not an option.
And unlike some others we discussed, here the system must maintain strong consistency for financial transactions.
Paramount. Prevents double charges, ensures accurate statuses, maintain data integrity. Strong consistency means everyone sees the same data at the same time.
Any inconsistency could lead to financial loss, legal issues, breach of trust.
Severe implications. The system needs acidity properties, atomicity, consistency, isolation, durability. Fundamental for reliable database transactions.
Beyond consistency, the system must guarantee durability with no transaction data ever being lost, even if things fail.
Reinforces that non-negotiable. Zero data loss for financial records. Every single transaction must be accounted for, safely persisted.
And the scale is huge. Scalable to handle high transaction volume, 10,000 plus transactions per second, TPS, and potentially bursty traffic like holiday sales.
Massive throughput demands, plus handling unpredictable spikes without degradation. #3. Core entities.
Let's define the core entities. First, the merchant entity.
Stores info about businesses using the platform. Identity details, bank info, crucial API keys for integration.
Next, the payment entity. Represents a payment request for a specific amount.
Right. It tracks the entire life cycle of a payment attempt, from creation to final success or failure.
And related to that is the transaction entity.
Represents an actual charge or refund against a payment method. Includes amount, status of that specific charge, timestamps.
And the relationship is one payment can have multiple transactions.
Exactly. If an initial charge fails and is retried, or partial captures or refunds, each is a separate transaction linked to the original payment. Provides a complete audit trail, #tag4 API or system interface.
Let's look at the APIs. To initiate a payment, a POST request to create the payment.
But crucial security note here. We would never pass raw card details directly to our backend. Never.
Right. Instead, use a secure tokenization process. Protect sensitive data. Fundamental principle.
Absolutely. Then for merchants to check payment status, they can use a GT request.
Or, you mentioned webhooks, as an alternative to polling.
Yeah. The merchant provides a callback URL. Our system POSTs to it when payment statuses change. Gives them real-time updates without constant polling. #tag10.5. High-level design.
Let's outline the high-level design, starting with how merchants initiate payment requests.
We have a payment service microservice responsible for creating and managing payments.
It talks to a central database storing payment records, status, amount, currency, metadata, and merchant info, API keys, business details, config.
Right. And it's important to clarify, at this stage, no actual charging has happened yet. We've just recorded the merchant's intent and created a reference for tracking.
Okay. Next, for users to pay with credit debit cards, we introduce the transaction service.
Responsible for receiving card details, via tokenization, remember, and managing transaction records throughout the payment lifecycle.
And crucially, it interfaces with the payment gateway, the connection to external networks like Visa, MasterCard, banking systems.
Exactly. The payment gateway connects to the right network, sends the authorization request, receives the initial response, approval decline.
Sends that response back to our transaction service.
Yep. And importantly, the gateway continues to listen for callbacks from the payment network over a secure private connection for status changes like settlement, chargebacks, etc.
So payment processing is inherently asynchronous. Initial authorization is just step one.
Exactly. Full completion can take minutes, even days, due to fraud checks, chargebacks, settlement. Our system must handle this asynchronous nature by maintaining payment and transaction states, keeping merchants informed.
And these payment networks operate on private, secure networks, separate from the public internet.
Right, adds another layer of complexity and security. And remember, a single payment can have multiple transactions reflecting all these stages.
Finally, the system must provide status updates for payments.
The payment service can query the database for the current payment state, status, errors, transaction details, to handle polling requests.
But polling isn't ideal for real-time or high frequency.
No. So webhooks are the better way for push-based notifications. Eliminates polling, reduces latency.
And webhooks are server-to-server communication. Our server notifies the merchant server directly.
Correct. Via HTTP request to a predefined endpoint the merchant configured. #tag6. Deep dives.
Let's dive deep. First, the system should be highly secure, non-negotiable.
A key aspect is request signing. Ensures API requests are authentic, unmodified, not replayed.
How's that work? Public and private keys.
Combination of public API keys, identifies merchant, and private secret keys for time-bound signatures. Merchant gets both during onboarding, keeps the secret key secure on their server.
And for each API request?
Merchant server generates a digital signature, hashes request details, method, endpoint, params, body, a timestamp, a unique nonce using their secret key. Signature sent with request. Our system verifies it.
Okay, another crucial security measure is the iframe solution for handling sensitive card data.
Yes. Mitigates direct exposure to merchant systems. Our payment system generates encryption key pairs. Our JavaScript SDK uses the public key for encryption.
And the iframe is served from your domain, not the merchant's.
Critically, yes. Creates clear domain isolation. Raw card data flows directly from customer browser to our PCI-compliant environment, bypassing merchant systems entirely.
So when a customer types card details in the iframe,
Our JavaScript SDK immediately encrypts the data using the public key before it leaves their device. Card data never exists unencrypted outside the browser.
so even if the merchant's site is compromised, attackers only get encrypted, undecryptable data.
Exactly. And merchants only receive a non-reversible token representing the card data. They store and use this token for future charges without bringing their systems into PCI scope. Reduces their compliance burden massively.
Wow, okay. Next, deep dive. The system should maintain strong consistency for financial transactions. Two facets, internal and external.
Right. Internal consistency. All our services, payment transaction agree on state, easier to achieve. External consistency. Our system accurately reflects what happened in external payment networks. Much harder.
How do you get internal consistency?
Use traditional database transactions with ACD properties. Keep payment and transaction data on the same DB node allows atomic updates. Both succeed or both fail. Use synchronous replication so all replicas have same data view before confirming success.
And for the bigger challenge, including external consistency.
We can move to an event sourcing architecture. Instead of just storing current state, record every state change as an immutable event in a chronological log. Creation, authorization, capture, each generates an event.
You'd use Kafka as the log.
Typically, yes.
Yeah.
Kafka is the immutable transaction log. Its durability and ordering are key.
So the overall flow with Kafka.
Payment and transaction services are producers, writing events to Kafka on state changes. Kafka durably stores events, immutable and ordered. Dedicated consumer services read events, update corresponding DD tables. payment transaction.
So the database tables become read-optimized projections of the event log.
Exactly. Used for serving API queries. And a huge benefit. If the DB gets corrupted, rebuild it by replaying the Kafka event log.
Okay, but how does that help with external consistency, aligning with Visa, MasterCard?
For that, you need a dedicated reconciliation service. Periodically compares our internal transaction records with payment networks records.
Finds discrepancies, like we show pending, network shows approved.
Right. When discrepancy is found, the service generates new events to align our internal state with reality.
How does it check the networks?
Networks expose two ways. One, direct API queries for real-time verification of individual transactions. And two, batch reconciliation files with comprehensive records for a period, usually daily.
Okay, let's talk scalability. Scalable to handle high transaction volume, 10,000 plus TPS.
For servers, all services are stateless, scale horizontally with load balancers. Fundamental.
Kafka. Cluster supports millions message a sec, but individual partitions handle maybe 5K, 10K message a sec.
Right, so to meet 10K TPS, need multiple partitions, likely 3.5 for throughput and fault tolerance.
Wait, a strategy.
Several techniques. Cold storage, move old transactions 3 to 6+ months to cheaper storage, S3 GCS, reducing active DB load cost. Read scaling, implement read replicas. Most payment queries are reads. Caching, use read as memcached for frequently accessed data, recent statuses. Write scaling, if needed. Consider DB sharding by merchanted or time-based partitioning.
And finally, how to support webhooks for push notifications.
Merchants provide two extra things, a callback URL, where we post updates to and subscribed events, a list like payment.succeeded, charge.failed they care about. We notify them at their URL when subscribed events occur. Real-time, push-based updates.
Now let's explore a foundational component of many robust systems, the rate limiter.
Ah, yes, the gatekeeper. Imagine a public API goes viral, or a bad actor tries to flood your services with requests.
How do you protect your infrastructure, ensure fair access, and prevent one noisy neighbor from ruining things for everyone else? That's the rate limiter's job. ###1. Overview and goals.
A rate limiter acts as a gatekeeper for a service, controlling the rate of incoming traffic from any given client.
Primary goal: ensure system stability and fairness. Prevent any single client overwhelming shared resources, the noisy neighbor problem.
Exactly. This design outlines a highly performant, scalable, fault-tolerant rate limiter. It enforces limits based on configurable rules. Requests exceeding thresholds are rejected or throttled. Protects the back-end service from overload.
The token bucket algorithm seems ideal here. Simple, memory efficient, handles bursts gracefully.
It is. Ideal choice. Each client gets a conceptual bucket with two properties. Bucket size, max tokens held, defines max allowable burst, and refill rate, rate tokens added, for example, 10 sec, defines sustained allowed rate.
Okay, how does it work?
Request arrives. Check if client's bucket has at least one token.
If yes.
Consume a token, allow the request.
If no tokens.
Throttle. Reject the request. Meanwhile, the bucket is continuously refilled at the refill rate, up to the max bucket size.
The aha moment here is it lets clients save tokens for short bursts without exceeding their long-term average rate, maintains fairness but allows flexibility.
Precisely. Handles bursts naturally. ###3, high-level architecture.
Important point. A rate limiter isn't a standalone service users hit directly, it's middleware. Executes on every incoming request before it reaches core application logic.
Right. Throttling happens at the edge, protecting downstream services. Two primary deployment models.
First, integrated library. Rate limiter included as a library in the application code itself.
Yep. Lowest latency, co-located. Drawback, requires language-specific implementations.
Second, sidecar daemon service. Runs as a separate process on same host or nearby. Application makes a lightweight network call, like gRPC, to it.
Correct. Benefits. Language agnostic, decouples rate limiter lifecycle from application, update scale independently. For our design, let's assume a distributed environment. Multiple service instances behind a load balancer.
Let's get detailed. Start with a single node rate limiter.
On one server, it's straightforward. Use a thread-safe in-memory hash map.
Key is client ID, IP, API key. Value is a token bucket object. Current tokens, last refill timestamp.
Exactly. Operation. Quick lookup, atomic token update, decision. Extremely fast, but insufficient for distributed systems.
Right. Which brings us to the distributed rate limiter. The challenge: requests from same client can hit different servers. Need a shared, consistent token count across the cluster?
The most robust solution. Use a centralized high-performance key value store like Redis.
Okay, so the data flow and implementation with Redis?
1. Request for client-told user123 hits server A.
2. Server A calls centralized Redis instance to check rate limit.
3. Crucially, it doesn't just get sick. It uses a Lua script sent to Redis. Why?
Atomicity. Lua scripts execute atomically on Redis, ensures the read-modify-write cycle for a client's counter is indivisible, prevents race conditions.
Exactly. Prevents race conditions in a distributed environment.
4. So the Redis logic, inside the Lua script, retrieves current token count and last refill timestamp, calculates tokens to add based on refill rate and time elapsed. If enough tokens decrements count, returns allow, otherwise returns throttle.
5. Decision. Server A gets response, processes request, or returns HTTP 429. Too many requests.
Makes sense. Why Redis specifically for this?
In memory speed, low latency critical path, atomicity, Lua scripting or built-ins like INCR prevent race conditions. Scalability can be clustered for high throughput.
Right.
Hashtag 5. Rule management.
Important. Rate limiting rules, e.g. client X gets 100 request min on search, are not hard-coded, right?
Absolutely not. Rules stored in a persistent database. PostgreSQL, DynamoDB.
A separate configuration service provides a UI or API for service owners to manage rules, adjust limits without code deployments.
Correct. And each application server runs a background agent that periodically pulls latest rules from DB and caches them in memory.
Avoids a DB query on every request. Improves performance, reduces DB load.
Significantly.
Yeah.
Hashtag 6. Key considerations and trade-offs.
Let's hit some key considerations. Fault tolerance. What if Redis goes down?
System should fail open. Allow requests to pass without rate limiting temporarily.
Why fail opened?
Denying all traffic, failing closed, is usually worse for overall availability than temporarily allowing some excess traffic. Could cause a complete outage.
Okay. Accuracy versus performance. Centralized Redis is highly consistent, but extreme network latency could cause minor inaccuracies. Allow a few extra requests before sync.
Potentially, yes. Generally an acceptable trade-off for the high performance gained in most rate-limiting scenarios.
Memory efficiency. How to prevent memory filling up with inactive clients.
Redis entries need a time to live, PTL. Automatically evicts old records after inactivity. Keeps memory footprint manageable.
And finally, client behavior. What should throttled clients do?
Ideally, use an exponential backoff with jitter retry strategy.
Wait progressively longer, add random delay, jitter, prevents the thundering herds of retries hitting simultaneously.
Exactly. Prevents exacerbating an overload and causing cascading failures.
Next up, a truly complex and fascinating challenge, designing a stock trading platform like Robinhood.
Yeah, this one requires incredible speed, absolute precision, unshakable reliability. Imagine a trading day. Millions of users checking prices, placing orders, blink of an eye.
How do you deliver real-time data, guarantee every order is handled correctly, even when the market's moving at lightning speed? Hashtag overview.
Right, so the system is a stock trading platform, Robinhood-like. Core purpose, enable users to view live stock prices and manage orders, market limit, create, cancel.
Scope is focused. Core features. Live prices, basic order management for stocks.
It's exactly. Explicitly excluding ETFs, options, crypto, full order book, after-hours trading, keeps the design focus for today. Hashtag 1. Functional requirements.
Functionally, at its core, live prices. Users view real-time stock prices. Fundamental.
And crucial, order management. Users create cancel market limit orders, view their order status. Hashtag 2. Non-functional requirements.
Non-functional requirements. Super stringent for finance. Consistency. Strong consistency for order management. Accurate, universally agreed upon order state always.
No room for error. Even momentary inconsistency can have big financial impact. Latency. Critical. Price updates, order placement 200 meters end-to-end. Delay means missed opportunities, bad prices.
Scalability. Support 20M daily active users, DAU. Handle 100M trades day, 1K trades AVG, peak 10Ks. Manage 10K symbols.
Efficiency. Minimize exchange API connections. They're costly, often charged per request, strict rate limits.
And reliability. Absolute. Handle failures without losing any order state. Every order accounted for, accurately reflected, even during outages. Hashtag 3. Scale estimation.
Quick scale estimations. Users. 20 ME DAU, 5 trades user day, a 100 meter trades day, a 1K trades AVG, peak 10Ks.
Symbols. 10K stocks, 1K update symbol, peak 10Ks. Orders. 100 orders day, X 50 bytes order, 5 GB day, 2T buyer.
Price updates, 10K symbols, X 1K updates. In staggering 10 million updates flowing in.
Key insight. High read prices, moderate write orders. Consistency is critical, especially for orders. Hashtag 4. API design.
Okay, API design. RESTful APIs with JW key for authentication. JWT is compact. URL safe way to represent claims, common for auth.
1. Get symbol price. GET, symbol name, header, authorization, bearer, JWT, returns, JSN on, symbol.string, price instance.long, market limit, price instance, long for limit, dotty.cm.symbol.string position, market limit, vice to lane shares instance n.
Returns.order, string status.string. Places market limit order.
3. Cancel order, delete order, authorization bearer, JWT, returns.
Okay, cancels pending order. 4. List orders. Get T orders. Header, authorization. Bearer, JWT. Query. Page any size int. Pagination. Returns paginated list. Orders. Orders, symbol, status, and us. Views, users orders. Hashtag 5. Database.
Database choices, given the strict needs, combination of tech.
Yep. Data. Postgres for orders. ACD, consistency vital. Cache. Redis for prices, low latency. Metadata. DynamoDB for external order mapping, fast lookups. Q. Kafka for trade feed, durability.
Key entities, user name, funds, symbols.
Symbol, ordered, user, symbol type, position, price, instance, num share, status, external ordered, exchange ID for our order. Trade, trade ID, symbol, price, instance, num shares, ordered.
Indexing strategy.
Postgres, PK ordered. Index on userid for lifting orders, partitioned by userid scalability.
Redis.symbol.price.symbol, hash, price timestamp, symbols.pubsub channel.
DynamoDB, PK external ordered, value ordered usered, quick lookup internal order from external ID.
Kafka, topic trades, partitioned by symbol, parallel processing, hashtag 6, high-level design.
Overall architecture, microservices, PubSub for prices, partition DB for orders. Components.
1. Client, mobile web app. 2. API gateway, routes requests, auth, rate limiting. 3. Symbol service, manages live prices, subscriptions.
4. Order service, creates cancels orders, syncs with exchange. 5. Trade processor, processes exchange trade feed, updates orders. 6. Database, Postgres, orders.
7. Cache, Redis, price subs. 8. Metadata store, DynamoDB, external order lookups. 9. Q, Kafka, trade feed buffer. 10. Exchange, external API, order placement, trade feed.
Data flows, price update, exchange of Kafka, trade processor, Redis, symbol service, eWay, SES.
Order create,
Yoki
client API gateway, order
Yeah.
service, EKI order service, they AboDB, stores mapping.
Order list, client API gateway, order service, Postgres exchange, client confirmation.
Order list, client API gateway, order service, Postgres AI client.
Visually, client talks to API gateway. Gateway directs to symbol or order service. Order service hits Postgres, Exchange, DynamoDB, Exchange feeds Kafka, Kafka feeds Trade Processor updates Redis, DynamoDB, Postgres, Symbol service pushes updates to client, interconnected flow for real-time trading, hashtag 7, deep dives.
Now for the deep dives, addressing those tough non-functional requirements. First, how do we scale live price updates? 10M updates to millions of users, 200 meters latency.
Solution components, PubSub, Redis, use Redis PubSub, channel symbol.pubsub.symbol per symbol, symbol service subscribe to symbols users care about, trade processor publishes updates to Redis.
Fan out SSE, symbol service maps, symbol to set to thread subscribed, pushes updates via SSE using HTTP2 to clients.
Scaling, shard symbol service by user ed, 100 servers needed. Redis cluster, 10 shards, 1M op shard capable. Load balance SSE with sticky sessions, consistent hashy routes clients to correct symbol service shard.
Optimization, batch updates, 10 meters intervals, reduces overhead. Drop updates for inactive clients, heartbeat mechanism.
Back of envelope. 10M updates, 10 shards equals 1M update shard, Redis handles. 20M users, X, 10 symbols, G sub, F's 1K update, 200 millubs bandwidth, manageable.
Why these? Redis pub sub scales subs well. SSE lightweight for one-way push. Sharding distributes load. Alternatives. Polling, high latency. WebSocket, higher overhead for mostly one-way.
Next, how do we efficiently track order updates and sync state with the exchange trade feed? Status changes fast.
Solution, metadata store, DynamoDB. Store external order mapping to ordered, userid lookup. Populated when order created, exchange gives its ID.
Trade processing flow. Kafka topic trades buffers exchange feed, partitioned by symbol. Trade processor consumes from Kafka, looks up external ordered in DynamoDB, gets internal ordered userid, updates Postgres order via userid order, uses sharded design.
State management. Define order states. Pending, submitted, filled, canceled, failed. Partial fills, update num shares remaining in Postgres.
Back of envelope, 10K trades at 1KB at 10 millibs, Kafka handles, 10K lookups, DynamoDB scales, 10K writes on 100 shards equals 100 write shard, Postgres handles.
Why these? DynamoDB equals fast mapping. Kafka, durability buffering. Postgres, strong consistency. Alternatives. Postgres index on external ordered, slow across shards. No metadata store. Slow full scans joins.
Final deep dive. How ensure order consistency despite failures? 200 meters latency, arguably the hardest part.
Create order workflow. 1. Write pending order to Postgres, userid shard. 2. Submit order to Exchange, sync call, get external ordered. 3. Write external order to DynamoDB, update Postgres status submitted. 4. Respond to client.
Cancel order workflow. 1. Update Postgres status pending cancel. Send cancel request to Exchange. Sync. 3. Update Postgres status canceled on Exchange confirm. 4. Respond to client.
Failure handling. Store failure Postgres write fails. Fail fast, client retries. Exchange failure during submit. Mark order failed in Postgres.
Post-exchange failure. Crucial. Implement a cleanup job. Periodically scans for pending or pending cancel orders stuck. Queries Exchange using client ordered. Pass during submit. Gets true status. Updates internal Postgres state accordingly. Runs frequently. Every 1 min.
Back of envelope. 10K orders. A3 writes. Create. PG DTB. PG update equals 30K writes. PG DDB scale. Cleanup. 1K stock orders day. S1 query equals 1K sex day. Negligible load.
Why these? Postgres is ACID. DynamoDB decouples lookups. Cleanup job, essential for resolving inconsistencies from distributed transactions external systems, ensures eventual consistency. Alternatives. No cleanup. Stale inconsistent states are bad. Pure queue for create. Higher latency for user confirm. Bad.
Okay, our final deep dive takes us to a more personal yet equally complex system, designing a fitness tracking app like Strava.
Yeah, imagine you're out on a long trail run, miles from any signal, but you need your app to track every step, every mile accurately.
And later, back online, you want to share your achievements, see your friends' activities seamlessly. How do you build a system that gives real-time local feedback, works offline, and scales to millions sharing their journeys? Hashtag tag overview.
Strava, popular fitness tracking app. Record shares physical activities, running, cycling, provides detailed analytics, performance routes, enables social interactions, build community. Hashtag tag1. Functional requirements.
Functionally, core stuff. Users should be able to start, pause, stop, and save their runs and rides. Life cycle management.
While running cycling, users should view activity data. Route, distance, time, real-time feedback to the athlete during activity.
And afterwards, users view details of their own completed activities and their friends' activities. Personal history plus social sharing viewing. Hashtag tag2. Non-functional requirements.
Non-functionals. Systems should be highly available. Availability consistency. More important, the app always works, records activity, than having strict real-time consistency for every data point syncing instantly. Users need to record without interruption.
Critical. Apps should function in remote areas without network connectivity. Vital offline capability. Outdoor activities often lack signal, must capture stored data.
Apps should provide accurate, up-to-date local statistics during run ride. Immediate, reliable feedback directly on device, regardless of network.
And scale to support 10 million concurrent activities. Massive challenge handling concurrent recordings from large user base on device plus backend sync. Hashtag tag3. Core entity.
Core entities. User, person using app, profile info, settings.
Activity. Individual run ride. Type, start and time, route data, GPS coords, distance, duration.
Route, collection of GPS coordinates recorded during activity. Could also be a field on activity entity.
Friend, connection between users for sharing activities. Friend management out of scope, but concept needed for sharing. Hashtag tag4, API or system interface.
APIs. Create a new activity. POST endpoint to initiate activity on server.
Update state of that activity, PKICH request. Why? PACH.
Preferred over PUT because only updating subset of fields, see status running, paused. More efficient, less data over network, minor gain but good practice.
Update activities route and distance, API for sending updated GPS distance during activity, though mainly local, as we'll see.
Get activities. Get T endpoint for retrieving lists of activities. Partial activity type means return subset of fields. Limit network data for lists. Hashtag tag5, high-level design.
High-level design. Users start, pause, stop, save activities.
Clicking Start Activity. Client app makes post activities, specifies type. Activity service creates DB record, returns activity object.
Pause resume. PATCH activities.activityID with updated state. Activity service updates DB.
Save activity. Triggers patch activities.activityID with state complete.
Crucial point. How to handle activity time when pausing. Simple start timestamp and current timed start timestamp at end is wrong.
Problematic, yes. If user pauses, start timestamp doesn't change, elapsed time keeps incrementing inaccurately.
Correct answer. Maintain time via a log of status update and timestamp pairs. Like start, TS1, pause, TS2, resume, TS3, stop, TS4.
Exactly. Calculate true elapsed time by summing durations between pairs, explicitly excluding pauses.
Oh, okay. Now, while running cycling, users view activity data, route, distance, time.
Use GPS coords to calculate distance via Haversine formula. Great circle distance on sphere from lat long.
But critically, the wrong approach is sending constant updates to server for this.
Explicitly state, wrong to constantly send updates to server for real-time display. The correct insight? Handle this logic locally on the client.
So app uses device location services, iOS core location, Android Fuse location provider client, to record GPS intervals, 2s, bike, 5s run, calculates distance, updates UI locally, ensures we get feedback, works offline.
Server sync happens later.
Finally, users view details of their own completed activities and friends' activities.
Flow. User goes to activities list page, client get activities.mode, user friend in page, gets list. List rendered. User clicks activity. Client get day activities.activity for full details.
Friends table. User add friended columns, bidirectional relationships, 2 entries per friendship, A, B, me, B, A. First column PK ensures efficient query for users' friends. Hashtag check tech 6. Deep dives.
Now for the deep dives. First critical challenge. How can we support tracking activities while offline?
Core idea. Record activity data locally on device, sync to server only when activity completes or user back online.
Benefits. Solves network reliability, saves bandwidth, provides accurate up-to-date local data, synchronies on device.
Steps. 1. On-device location services record GPS intervals.
Yeah.
2. Record event data locally in-memory buffer, array of GPS timestamp pairs.
3. Periodically persist buffer to device local storage, 10 secs, to prevent data loss, battery drain, shutdown. iOS core data user defaults, Android, room shared preferences.
4. Resumption. App reopens resumes. Check local storage, load buffer before continuing.
5. Single request sync, online. Activity complete online, send all accumulated data in one request, chunk if very long.
6. Background sync. Mechanism periodically attempts uploads when connection available, even if activity not complete, balances efficient site durability.
7. Local data deletion. On confirmation of remote DB save, delete local buffer. Key insight. Local tracking dramatically reduces backend load.
Next, how scale to support 10 million concurrent activities. Sounds massive, but...
Because tracking is local, backend request load is reduced maybe 100x, data sent once per completion. Simplifies backend scaling hugely.
Storage estimation per activity. Metadata, 100 bytes. Root data, most expensive. 30-minute avjg, GPS every 3's repods. Each point, lap plus long plus TS, total route, 15 KB.
Annual data. 15 KB activity, huge number of activities year, a 547.5 TBR, using source figure. Massive data volume.
Scaling strategies. Database sharding. Split data across DB instances. Shard by activity completion time, most queries recent.
Data tiering. Move older data to cheaper storage. Hot recent, fast expensive. Warm 3-spay Chermo, slower cheaper. Cold 1Y archival S3.
Caching. Introduce if needed for frequently queried activities. Reduce read load. Not initial priority, low read throughput expected, but first step if load times suffer.
DB choice. All popular major DBs would work. Microservices versus monolith. Given low expected read-write throughput after sync, no initial need to break into microservices. Scale service horizontally. Memory, CPU, network limits.
Next, how support real-time sharing of activities with friends, if tracking is local.
Reintroduce periodic server updates during activities specifically for sharing. Data flow. While local device handles user-facing data, location updates every 2 5s sent to server.
Server persists updates to DB, broadcasts to users' friends who are actively watching.
Polling mechanism more effective here than SSE WebSockets. Why? Updates predictable every 2 5s. Allows efficient polling intervals. Precision not critical. Few secs delay okay for friends.
Smart buffering system. Enhance UX. Intentionally lag displayed location data for friends by 1-2 update intervals, 5/10s. Creates smoother, continuous animation of movement.
Finally, how expose leaderboard of top athletes?
Leverage Redis in memory store. Use Redis sorted sets. Mechanism. User IDs and members. Total distances, scores, updates, new activity logged. Increment user score in sorted set. Querying. Retrieve top end members. Extremely efficient in Redis.
For country filtering. Strategy. Separate sorted sets per country. Leaderboard.run.USA. Leaderboard.run.Canada. Update flow. Log activity. Update global and country-specific leaderboards. Querying. Use appropriate country set. Caching strategy. Optional. Keep only frequently accessed leaderboards in Redis. Calc less common on demand if needed. Memory. Hashtag no tag outro.
Wow, what a journey. From the intricate world of coding platforms where security and real-time feedback are paramount,
To the fast-paced environment of stock trading demanding strong consistency and lightning speed.
and then the highly personal realm of fitness tracking that must work even offline. We've peeled back the layers on some truly remarkable system designs.
Yeah, you've seen the crucial decisions behind keeping financial transactions consistent, ensuring real-time comments flow seamlessly, and even making your run data accessible in the middle of nowhere.
What stands out to you, the listener? Perhaps it's the recurring patterns, like the strategic use of message queues for durability and buffering traffic.
Or the careful trade-offs between availability and consistency. that underpins so many of these systems. We saw how understanding user behavior like read-heavy live comments versus need for strong consistency in bids drives fundamental architectural choices.
It's a testament to the power of thoughtful engineering in building the digital world around us. Each system presents unique challenges.
Yet they often rely on similar building blocks. Smart database choices, asynchronous processing, robust caching, ingenious ways to handle real-time updates, and massive scale.
So, what problem will you decide to solve next, equipped with this new depth of understanding?
The principles we've unpacked today are the foundation for building almost any complex distributed system you can imagine. Keep that curiosity alive. Keep digging.
That's all for this deep dive. Join us next time as we continue to unravel the fascinating world of information.